is Hong He. He continued the lecture on the surfaceology. Please.
Thank you. Yeah. Okay, great. So let's first summary what we talked yesterday. I essentially give you this formula, explain to you what do I mean by this formula, that for any given surface S, there is a string formula associated with this surface called AS with alpha prime in it, which contain E edges. This edge is related to the number of external legs and loop order in this formula. And when I give a surface S, I already gave the base triangulation for this surface. So essentially that's the part of the definition of a surface, is that you draw it with a particular base triangulation. You can choose any one. The formula doesn't depend on which one you choose. It only depends on this surface itself. And then on this base triangulation, there are some roads, right? So for each road, I can put some integration variable y. For any curve on the surface, remember there's a lamination, so the curve actually goes from some road, some external road, and travel through some road and go out as some external road. For any curve on the surface, I can assign a kinematic variable x of this curve, which is given by the momentum of the curve squared. You can also put mass squared here. And this momentum of the curve is given by the rule that it's all from the momentum from the left when the curve turns right? And then the key thing is that there's this D-log form. Okay, this D-log form on this integration variables of this surface, and this product over all curves. So this is generically infinity. You know, for generic surf S, this is infinity, the infinite product of all curves with some u variable raised to the alpha prime xc. Okay, so the key thing in this formula is the definition of this surface with base triangulation, the definition of curve with kinematic invariance, and the most importantly, this object. This object is given by a multiplication rule of, for any curve, there's a word. Okay, just read off the road in whichever way you want. There's some boundary road, and every time it turns left or right, you record it. Remember, like when it turns right, I can draw it this way. When it turns left, I can draw it this way. And then you multiply the matrix. Left matrix is this, and right matrix for the particular for that specific y, right? The right matrix is this, right? So so this is the definition, and this is the word associated with the. Sorry, I think I wrote it wrong, right? So this is y011. Yeah. So for left turn and right turn, you put these 2x2 matrices, and you take the product of them. You define this MC for that curve, and then finally you take 1, 2 component, 2, 1 component divided by 1, 1, and 2, 2 component. That gives you the U of C. So remember, this formula we've known for a while. Like as I said, for the case of the disk with n marked points on the boundary, this formula is essentially the Kobayashi formula for n tachyon amplitude. You just shift their mass from the tachyon the mass square from 1 to 0, then you get this formula. Okay, and there's even this interpretation of the U in terms of the special cross ratios, right? So the Uij for the disk, the Uij is really the this cross ratio. So they satisfy the U equation. On the disk, we already know, I mean, from a long time ago, we know that 1 minus Uij is given by all the product of UKL where KL intersect IJ, right? So this picture that you have a chord IJ. So on a disk, remember on a disk there are only n times n minus 3 over 2 curves. That's the only case that strictly speaking, the only case the number of curves is finite. That's the disk with n-puncture tree level case, right? And then every curve is labeled by this endpoint I and j. And the U equation tells you that 1 minus any of these Uij is equal to the product of all the UKL crossing it, everything crossing it. Okay? So that's the key to factorization. So I think I should emphasize this again that, so let me, yeah. So of course this generalized to all surfaces. That's the new thing. That's the thing people realize in the last 3 years or so. And also the U equations in general looks like this. 1 minus any curve is product of all curves where you have the product of all curves raised to the power of the intersection number between two curves. Now on a general surface, not on the disk, those curves can intersect several times, right? Not only once. So there's a precise definition. I don't want to go into detail, but there's a precise definition given the word of C and word of C prime. You can do a combinatorial counting on their words to determine what's the intersection number. And this is the general thing. This is a remarkable formula that it exists for any curve on any surface. The U variables can satisfy this. This equation, first it has solution, so this exists. And the solution space is d-dimensional, or e-dimensional for the number of edges on the curve, which is our dimension of the integration region, right? So it has a e-dimensional solution space. That's really the remarkable thing. And this formula, it looks very simple. I just give you some base triangulation y and say u of y is given by this simple rule. There's a very deep mathematical theorem behind it which guarantees it works. So once you find uc of y in this way, it will satisfy this equation. That's the part I omit, which amounts to hundreds of pages of proof and all the relation with the Quiver representation theory. And I mean, for example, in 2019, when we first tried to generalize this idea of binary geometry, by the way, this is called binary geometry. When we first tried to generalize this idea to loops, we had no idea that we need to deal with surface, with infinite number of curves and so on. We thought about it in a different way, because on the disk, let me write down the disk formula for you, right? Just on the disk, this is the famous string formula. Let me first write this down, which you have for any triangulation of the disk, any base triangulation of a disk, you have this variable, and then you have your Uij, and call it A. This A from 1 to n minus 3 gives the triangulation of your disk. I mean, anyway, just like that. That's a triangulation of 5-puncture disk. You can do it in any way, in any triangulation. And then there's the formula of Uij as a function of y raised to the alpha prime xij. This is the tree level case. So this can be rewritten in this way. I think I showed you yesterday. Sorry, this is n minus 3, more concretely. It can be written as product of this y, because every Uij, when the ij is one of when the ij is the same as a variable in the base triangulation, I mean as one chord in the base triangulation, the Uij will be proportional to y. So you can immediately write down this part. There's a part. I mean, this A labels the base triangulation. There's this part. There's the part that you raise this y to some power proportional to alpha prime. This part regulates the possible divergence at 0. Okay? So this all integration variables goes from 0 to infinity, so that you see from here that all the u's are between 0 and 1. And that's why the binary property, when one of the u goes to 0, all the crossing u goes to 1, the whole system decouple. I mean, people like to call it factorization. That's not precisely right. I mean, at tree level or at in general surface with such a curve that goes from external to external, it looks like factorization. But it also includes this kind of case, right? So when this U, that it connects an external one to an internal loop puncture, when this U goes to 0, it's not factorization, it's really the single cut of a higher loop amplitudes into lower loop amplitudes. Okay? So most generally, when a U of C goes to 0, this amplitude A alpha prime of S goes to, I mean, okay, really what I do is when X goes to 0, when external X, because U's are, this U and Y are internal integration variables, so the amplitude really depends on all the X's, right? And when I choose one of the X goes to 0, the integral develop a pole there. And you can compute the residue of the pole, because the residue of the pole is given by the corresponding U goes to 0 region, where you see the surface actually become the S, like remove this curve, right? So essentially at tree level it's like factorization, or at loop level this is like single cut. So there's a very systematic way of writing down this residue for any. So this is amplitude. This is exactly what we've been taught about string amplitudes and the field theory amplitude, is that at least for string amplitude we consider the field theory poles is that they start to do these things on every singularity we want, right? On massless poles it factorize or go into single cuts. And at tree level it's very special that we can write down explicit formula without talking about anything else. So this factor is part of the special U that's coinciding with the base triangulation. It pull out this factor. So there's a regulator regulating everything at 0. Okay? So that's why when this regulator is removed, when XA goes to 0, there's a singularity. It's no longer regulated at 0, this integral, because this guy is the canonical form that has logarithmic singularities on all the boundaries. All the boundaries means that any U can go to 0. So naively you have only n minus 3 y, but there are many ways they can approach 0 or infinity, such that you are really approaching all this n times n minus 3 over 2 boundaries of the isosahedron, right? So really this form has singularities everywhere. So this factor only regulates divergence at 0. And there's this so-called F polynomial. They are the function of y, and they are raised to this power Cij, where ij goes to this n times n minus 3 over 2 minus n minus 3, because you already pull out n minus 3 factor here. Okay? So at tree level, it's a much cleaner story that since there's no infinite product, all the U's are very simply written as the base ones that are proportional to y and the rest. And then there are dependence on, because every U is this ratio of some polynomial. So I can rearrange their polynomials such that this becomes just a polynomial Fij, right? So yesterday I gave you this Ray-like situation. We have 1, 3, 1, 4, all the way to 1, n minus 1. In this triangulation, I even give you explicit formula of Fij, because now the y are labeled as y1a, right? So I mean, let's just call it ya. For every curve that a goes from 3, 4 to n minus 1, I omit the starting point 1 because everyone starts from 1. So this, I give you the formula that is given by 1 plus yj minus 1, all the way to yj minus 1 down to yi plus 2. Okay? Remember, this is the formula. If I give you this formula, then this becomes explicit. There's nothing, no detail I haven't told you. I mean, remember, this Cij is given by xij plus I plus 1 j plus 1 minus ij plus 1 minus I plus 1 j, right? So this is the so-called ABHY condition. Okay? So for tree level, things are particularly clear. So I really encourage you to play with these things that if you choose a Ray-like triangulation, you are done because you don't need other triangulations. They're all equivalent. In this triangulation, I give you the explicit formula. Now you can play with this. And when you play with this, I mean, I also recommend you to look at this earlier paper we had, which is, I mean, I give you some reference yesterday. Let me write it again. So these are what I've talked this so far, mostly based on this paper, which talk about all loop scattering based on a counting problem. And today I'm gonna talk about two papers from last December, which is telling you how to go from chase phi cube to other theories, like more realistic theories like Yang-Mills and But I also encourage you to look, maybe not at the original paper of ABHY, but this paper from several years ago. This is called stringy canonical form. This is more like a math paper. It tells you that for any integral of this form, so for any integral where you have some positive parameter integrated from 0 to infinity with this regulator regulating divergence at 0, and some positive polynomial, any positive polynomial raised to some negative power, there's a theorem. There's a theorem telling you how this integral, where do this integral converge, and what's the alpha prime to 0 limit of the integral. I don't think I explained clearly how to take alpha prime to 0 limit of this string integral for general surfaces. That's a very difficult problem because it's meant to incorporate all the Feynman diagram, including mapping class group being modeled and so on. But at least you can look at that paper to understand what's the gist of taking this limit, right? So when you take the limit of a general integral of this form, it's very simple. The result of this, let's just look at tree level. The result of this tree level string integral is given by the so-called Minkowski, the canonical form of so-called Minkowski sum of Newton polytopes. I mean, I give you a lot of word, but you should. I'll explain. Yeah, the Newton polytope of this Fij with this function with this variable is given by x. Yeah, given by this xa. So this is the Minkowski sum of Newton polytopes. Okay. This is nothing but another way of saying tropical limit. Okay. So for general surface, you can also use this. The only difference is that now there are infinite number of Newton polytopes. So what are Newton polytopes? If I give you this polynomial like that, if I give you some positive polynomial, the Newton polytope is given by the convex hull. The convex hull of, so a Newton polytope of a polynomial is given by the convex hull of all these exponent vectors of the thing, right? So if the convex hull of the exponent vectors. So for example, if I give you, let's see if there's a good example I can show in real time. So like for example, I give you 1 plus x squared y plus something. So the exponent vector here is just 0, right? Since I'm in two-dimensional space, 0, 0, and this one is just 1, 0. This one is 2, 1, and so on, right? So I'm just taking the convex hull there. This is the origin, this is 1, 0, this is like 2, 1 here. This is 2, 1, this is 1, 0, this is 0, 0, and I'm taking the convex hull. For example, you can have many other terms, then you include more points and take the convex hull. And then the Minkowski sum is just really taking the collection of all vectors that's given by the sum of these vectors in its summand, right? So I hope this is very clear that the ABHY isotropy can be understood in this way. So for example, if you look at our Rayleigh triangulation, every F polynomial give you a Newton polytope which is trivial. It's a simplex. It depends on how far away ij are. I mean, let's even go to like 5 point. Let's write down 5 point very explicitly. Okay, A5. I mean, I'm giving you essentially a review of ABHY from this point of view. So in general, for any surface, it's the same way of taking field theory limit. Yesterday I told you about a G vector picture, but the dual of that is this surface hedron or Minkowski sum picture. So at 5 point, I mean, let's look at this dy3, dy4, Okay? And there's two-dimensional integral, right? So I have alpha prime squared here. And I have, okay, also y3 raised to alpha prime x13. Remember, I'm doing, for 5 point, I'm really doing this triangulation actually. 1, 2, 3, 4, 5, right? This triangulation has a picture like that. 1, 3, 1, 4. Those two are my base variables. So this y3, y4 are just these two, y13, y14. So their exponents are x13 and x14, respectively. And what are the f polynomials? I think I also showed you the f polynomials yesterday. I thought I made a typo there. There's no typo. I just misunderstood. I mean, it's all fine. So let's look at this product of Fij there. So I should have f. What are the range of Fij? I mean, there are those that not including j equals n or 5 here. So we have 3 f polynomial, f13, f14, and f24, raised to c13, c14, and c24. That's it. That's a 5 point. I mean, let me even write down more explicit for you. f13, according to this formula, would be 1 plus y3, right? f24 would be what? 1 plus y4, because you see here the thing always starts with 1 plus y4, and it should be y4, y3, all the way to y4, yi plus 2. So when I is 2, there's just a single term, y4, right? When this is 1, 3, then you have 1 plus y3 to start with. But I'm talking about, sorry, 1, 4, then you start with y4. Sorry, 2, 4, you start with y4 and you end. But 1, 4, you can start with y4 and then y4, y3. That's I plus 2 is 3 now, right? So for f14, you have this slightly interesting polynomial, which looks like y plus 1 plus y4, y3. Sorry, raised to this power. Okay? So if anyone asks you what's the 5 point disk integral, that's it. Don't use z. You'll break my heart if you use z. Just use this positive parameterization. It manifests a lot of properties. Okay? So one property is that what's the alpha prime to 0 limit? Now you can use this formula. So the Newton polytope of this guy is a line interval in the y3 direction, right? Because the exponent is 0, 0 and 0, 1, 0. And the Newton polytope of this guy is a line interval in y4 direction. Okay, so if we have something like this, y3, y4, the first one gives me here from 0 to 1. The second one gives me, the third one gives me y4 direction. This line interval. The first one gives me this line interval. And the middle one is what? The middle one is given by this point, and this 1, 1 point, right? The exponent is 1, 1. So the third one is a triangle. Okay? So I'm always very bad at doing Minkowski sum, but let's try it. So remember, I should also say here when I do Minkowski sum, this Newton polytope there is a convex hull of those exponent vector, which are basically just 1 or at most 2 and this kind of integer. So when I take the Minkowski sum, the size of this polytope is determined by Cij, right? I have to scale it by Cij and then sum take the convex hull of all the vectors in it. Okay? So I'm really doing this. I'm really doing this first one not with size 1, but with size C13. This second one with size C24, and this middle one with size C14. I'm really doing a Minkowski sum of these 3 objects. What's the result? The result is this. Just do this exercise yourself. Try to put these things together. Sorry, maybe I made a mistake in drawing the middle one. Yeah, somehow the middle one in my notes, I mean in our paper is drawn this way. Or maybe, okay, sorry, that's just a rotation. Sorry, in our paper, it's called this. Anyway, doesn't matter. If it's called this, then it's more like 0, 1, and 1, 1, right? Oh, sorry, it's exactly that. Sorry, I'm being totally stupid because this is y4. So y4 is really in this direction. So I did it wrong earlier. So it's literally this guy together with C14. So you obtain the ABHY polytope for the first non-trivial case. The 4 point is too trivial, right? So this y-axis is associated with 1,4 and x-axis is associated with 1,3. So you obtain this pentagon. I told you this is the first, this is the association for the 5-point amplitude case. And you see where exactly, for example, this size is C13. It's coming from here. And to this point, this is C14. And to here, this is C13 plus C14, right? So that tells you the precise definition of this. Of course, that's not what we originally written as ABHY. What we originally written is something I also mentioned yesterday that, sorry, maybe I write here, that you take all the xij plus I plus 1, j plus 1, minus ij plus 1, minus I plus 1j. You take this combination that we call Cij to be a constant. This equals a positive constant, right? And remember, in our base triangulation, which is 1, 3, 1, 4, and so on, this Cij must be, you know, like I smaller than j to n minus 1. It cannot reach n. Those j equals nk's are what we deleted, right? You can also see from here, I didn't have any C25, C35. Those are deleted. I'm left with this 1, 3, 1, 4, 2, 4. So what I told you yesterday is that if you impose the condition, this linear condition, intersect with all the xij being positive, you get the association. So that's the original definition that for n-point string amplitude, the field theory limit is given by n-point trace phi cube amplitude. So the n-point trace phi cube amplitude is given by the canonical form. Canonical form means that you just take only the logarithmic singularities on its boundary and recursively of this guy. So this condition defines you the n-3, the association of dimension n-3, the ABHY one, so the association of dimension n-3 here, which is nothing but summing over all the vertices. Because this is a simple polytope. I mean, I don't need to go into any detail, but just to tell you that for a simple polytope, you just go to any vertices of this polytope. And for any vertices, there are exactly d facets meets there, right? So you just take xi1 all the way to xid. In our particular case, this is I1, J1 to In-3, Jn-3. That's the Feynman diagram, okay? So ABHY is the first example in trace phi cube theory that achieved two things. One is that for trace phi cube, for field theory amplitude, the ABHY, the association picture tells you that all the Feynman diagrams are combined into the volume or the canonical form of a single object. But additionally, this single object, now you see it comes from this disk integral I told you. So that's the second thing, right? You write down a disk integral, which can be viewed as a string version of the association. And when you take alpha prime to 0 limit, just use the general theorem of this stringy canonical form paper, you get Minkowski sum, which also gives you this picture. Okay? So that's a review and also further explanation of the general surface integral and how to take its field theory limit. I mean, I only explained the tree level, but all loop cases are similar. The only difference is that at loop case, you have infinite number of summand to take into account. Of course, that only changes, like I showed you yesterday, the G vector approach somewhere, that only changes special places. The general picture is that very similar to tree level, you obtain some polytope whose canonical form give you the trace phi cube amplitude. So for example, in the 5-point case, this is really just 5 terms that looks like this, okay? 1, 3, 1, 4, 1, 4, 2, 4, 2, 4, 2, 5, 2, 5, 3, 5, and 3, 5, 1, 3. Okay, these are the 5 vertices of this isosahedron. Look, here there's a facet sitting at x14 equals 0. Right, let me even explain this. This is the facet where x14 equals 0, right? This is the facet where x13 equals 0. And what's this facet? If you solve the ABHY condition or take the Minkowski sum carefully, this will be the facet x35 equals 0. And this will be the facet x25 equals 0. And finally, this one, this 45-degree one, is the facet where x24 equals 0. Okay? So how do I obtain this volume form? I go to every vertex and take the n-3 facets meet there. Okay, so this 1, 3, 1, 4 is at the origin. This 1, 4, 2, 4 is here. 2, 4, 2, 5 is, sorry. Sorry, the 1, 4, 2, 4, sorry. 1, 4, 2, 4 is here. And 2, 4, 2, 5, 1, 4, yeah, the second term is actually sitting here. The third term is 2, 4, 2, 5, right? Is this one. And then this term is 2, 5, and 3, 5 meets here. And finally, the last one is 1, 3, and 3, 5 meet here. Okay? So you can imagine how to generalize this to any n, where you cannot visualize that higher dimensional polytope anymore, but it's the same thing. So that's really giving you a new derivation of the ABHY, which is also in this paper, tells you that the string formula can be regarded really as the alpha prime deformation of the field theory ABHY. Okay? The field theory isosahedron. So now let's switch gear. I want to tell you some property revealed by this formalism already at tree level, but then you immediately realize this property, which include some hidden zeros and the factorization near zeros for the phi cube amplitude and their stringy phi cube amplitude. But also this property will suggest that there's a unity. So I'll talk about two things. One is the hidden. I mean, in the rest of this talk, I'll talk about some hidden zeros and also factorization near zeros. So this is very surprising because we usually only talk about factorization when you're at a pole, right? When you take some x to 0, you're at a pole. Of course, amplitude should factorize. Everyone knows that. But already even for tree level, including stringy phi cube, so that formula, for this formula, if I'm telling you this formula has many zeros, so not when x goes to 0. When x goes to 0, it diverges, right? It's the opposite. When some combination of x, actually, when some c, remember, c are combination of x, which represents non-planar Mandelstam, right? So when some c goes to 0, I'm telling you this amplitude will vanish, okay? A little bit surprising, but maybe not so much. But I'm also telling you that when you go near this 0, for example, you set a lot of c to 0, but one of them you turn it back on, no longer set to 0. This string amplitude, including the field theory phi cube amplitude, will just factorize. Yeah, this is what I wrote as field theory phi cube amplitude. It will factorize into products of lower amplitudes or lower currents. I mean, with lower point functions of the same form with shifted kinematics. That's very surprising. And more surprisingly, the same hidden zero and factorization apply to this two theory, nonlinear sigma model and Yang-Mills. Actually, strictly speaking, Yang-Mills scalar. This is for the 2n scalar amplitude. Okay, so that's yes.
About how you.
Sorry, yeah. You should ask a question. Yeah, sorry.
How you build the object in the first place. So you associated sitting in the other blackboard.
Okay.
Yeah, so I see that which Fij you associate with some objects. So I can understand that you have to combine them in such a way that the resulting object is a complex figure. But my question is, how unambiguous is this operation? Like, if I associate to each Fij something, and then I look for the figure that glues them together in a complex figure,
Yes.
is this operation guaranteed to be unique?
Yes. So for any choice of Cij, any value of Cij, this gives you the same polytope, except the size will vary, right? The size depends on which points in the kinematic space you have. So this is the key idea. I mean, if you look at all the kinematic variable, you imagine you live in a huge, this n times n-3 over 2 dimensional space. But now you choose this condition to reduce it down to n-3 dimensional. The key is that as long as you choose Cij to be some positive constant, any constant, then when you vary all this Xij, you're living inside that same shape. The shape is called a sociohedron. I told you the pentagon, the three-dimensional generalization for 6 points and so on. The Cij is kind of the moduli of this infinite families of a sociohedron, where when you vary the value of Cij, the size starts to change, the position of the vertices start to vary, but it's the same as sociohedron. Okay?
Yeah, no, okay, that's sure.
Yeah.
But then, like, how did you do the segments and the triangles?
No, this is called Minkowski sum, or you just solve those inequalities. So let me give you an example. Sorry. The 5-point example, I can write it very explicitly for you. So let me do it here. So this conditions looks like x13 is positive, x14 is positive. These two are my basic variables, right? Your question is, how do I glue them together? I can tell you that a more direct way, original way is that I don't need to because it's not so easy to visualize the Minkowski sum on the blackboard. So solving this equation is even easier. So you solve x24 using this equation. So what are these equations? These equations are just the C13 that equals 13 plus 24 minus 14. C14 is like x14 plus 25 minus 24, and the C24 is x24 plus x35 minus x25, right? You solve these three equations. You'll see that there's no issue with convexity or anything. So when you solve this, you find x24 being C13 minus 13 plus 14. For those of you who can still remember what I talked about G vector, you remember this G vector, right? G vector of x24 is G vector of 14 minus 13, or the other way around. So that's because the G vectors are the norm vectors of this pentagon. Okay? So you bear with me, you will immediately see what's going on. So x25 is given by C13 plus C14 minus 13. Also need to be positive. Finally, 35 is C14 plus C24 minus 14. Also need to be positive. So look at these 5 inequalities. Forget about Minkowski sum. Minkowski sum is I introduced this for some later purposes. But look at this 5 inequality. Now you do it again. If I ask x14 to be positive, I'm here, right? I'm on top of this line. I ask x13 to be positive, I'm on right side of this line. So I just keep solving. I have this, and this. So this line would be my 3,5 equals 0. This line would be 2,5 equals 0. And finally, this line would be 2,4 equals 0. The C doesn't matter. Any choice of C, as long as they are positive constant, always give me this picture. Okay? So there's nothing, when you start to vary this value of C, it just moves. These 5 lines start to move, but their relative position never change. This 45 degree and yeah. Very good question is because that is when C13, C14, C24 are positive. Now I'm going to tell you about this hidden 0 where I turn them off. I turn C13 to 0. Now you will see the association starts to collapse. So as long as they are positive, it's always this shape. And it's always given by the 5 term The volume is always this amplitude, nothing special, right? It's just the different, it's just moving. The axis never, axes are still called axis. But when some c goes to 0, this will move to here, for example, becomes a square, or keep moving, becomes a line, or going down becomes a triangle, and so on, okay? So this is what I'm going to talk about in the last 20 minutes, that these guys have hidden zeros. And so let's look at an example, 4 point. I mean, anyone is happy with 4 point, okay? So 4 point, I told you, so Heejun tells you this trivial formula. But now you can interpret this trivial formula in this way, because the 4 point condition is this, right? So this 2 term is really coming from two endpoints of a line interval, where this side is x13 equals 0. This side is c13 minus x13, which we call x24 equals 0. So you see, what's this one-dimensional association? This one-dimensional association is x13 between 0 and the c13, if you choose 13 to be your base variable, right? So everyone knows here, if I put the two denominator together, the numerator is 13 plus 24, which we call c13, right? So you say, okay, it has a 0. If we set c13 to 0, the 4 point amplitude vanishes. Okay, no big deal. And I should say that this comes from the 4 point Veneziano amplitude, where I have gamma x13, I'm ignoring alpha prime, gamma x24 divided by gamma c13, right? So what are the zeros of a beta function? Everyone knows the c13 equals 0, minus 1, minus 2, and so on, right? So I would say the 0 of field theory amplitude is contained in a special case of 0 of string amplitude. Okay, so far I'm saying things very trivial things. And now let's look at 5 point. Sorry, it's here, right? Tell me what's the 0 of this function? You say, okay, let's do the same thing. Let's put x13, x14, the 5 guys together, and I get a cubic numerator, right? 5 term cubic numerator. What's the 0 of this numerator? You solve this cubic equation. I mean, there's many things you can do. I'm not saying we exhaust all the 0, but it's really hard to find even one 0. Now, yesterday I introduced this picture, which is going to be very useful. So yeah, I should have joined earlier. So for 5 particle, all the x variables are sitting here: 13, 14, 24, 25, and 35, right? Remember, these boundary guys are like 1, 5. This is 1, 2, 2, 3, 3, 4, 4, 5. They are all 0. There's nothing for the boundary, right? So we just keep this 5 axis. And what is ABHY condition telling you? The ABHY condition is telling you that for every causal diamond here, for every square here, I put in the corresponding C according to the bottom guy. So this is C24 because the bottom guy is X24. I'm ignoring the axis, okay? I'm not to clutter my picture. So remember, this choice is corresponding to our Rayleigh base triangulation, and it picks out this 3C we want. We don't want any C with number 5 in it. And this picture makes it very clear that every C is given by the top at the top guy, bottom guy, minus left, minus right. So that's the condition I wrote here. Okay? There are 3 such conditions. You solve these 3 conditions, you express the remaining 3 guys in terms of the base 2 guys, you're done. The inequality carve you out this picture. So that's the thing. So can we learn something about the 0 in this picture? Or in this, I mean, it's equivalent in the inequality picture or in the Minkowski sum picture? Yes, we can. Let me just tell you the answer. The answer is that you look at this small rectangle, I mean, a rectangle that goes from this boundary to this boundary. So in this case, it will be C13, C14 equals 0. You look at this. I mean, of course, it's not enough just to set one C to 0 to make things vanish. You already see it, right? But you can set 2 C's to 0. Okay, I leave you as an exercise. Well, it's easy that if you set C13 to C14 to 0, you can literally check that this expression vanishes. I'm going to explain in a second why, right? But it's not obvious. I hope you understand that. And also, alternatively, I could choose this rectangle. In this picture, that's the only two rectangles I can choose to go from left to right. So I have a different set of conditions, C14, C24 equals 0. That also makes this cubic numerator vanish. Okay? Totally non-obvious already for this seemingly trivial case of 5 point, right? Of course, you understand that I'm choosing a particular base triangulation. This condition has their cyclic image, right? So for any like skinny thing, for any CI, for any like, so what's this condition saying? It's really saying P1.P3 and P1.P4 is 0. Remember, I didn't set P1.P2 or P1.P5 to 0. Why? Because they are the poles. So it's very important to distinguish between planar and non-planar Mandelsteins. These are non-planar Mandelsteins I set to 0, right? So now you can generalize already for 5 particle. This is setting particle 1 with any non-planar guys to be 0. This is setting particle 4 with any non-planar guys, non-adjacent guys to 0. So I can also generalize it to any other particle. So there are 5 zeros, 5 obvious zeros. I mean, 5 zeros I'll explain in a second. Now you can also look at 6 point, which may take a while to draw, but just give you the gist. That's 1, 3, 1, 4, 1, 5. So this will be C13, C14, C15. So I'm claiming, for example, the same skinny rectangle. If I have, this is to any number of points. If I have C13, C14, all the way to C1n minus 1, I set all this non-adjacent Mandelstein with P1 in it to 0. I'm claiming that's a 0. Actually, this is 0 we found in 2017. We didn't make a big deal of it, but that's also one thing we understand. And of course, you can also look at here, right? You can also look at this side, C15, C25, C35. That's also a 0, right? So for any number of particles, this is a condition. For 6 particles in particular, you can look at these 2 skinny rectangles. Now there's something new. Yeah, I had to use yellow now. But there's something new. You can look at this rectangle or square, which also go from left to right. This has these 4 guys, C14, C15, sorry, C24, C25. If I set these 4 guys to 0, not 3 guys, things in the yellow, sorry, I mean, I should write it in yellow. If I write these 4 guys to 0, the amplitude also vanishes. I mean, it's very non-trivial from Feynman diagram because now the 6-point amplitude, the volume form of a 6-point amplitude has 14 terms. Each term looks like 1 over x, right? This is the triangulation of hexagons, the Catalan number I told you. So how do we explain these zeros? Okay, it's very simple. It's in this Minkowski sum picture. So we can show that, I mean, I'm not gonna go into detail here, but just to say the very least that when you set a rectangle that goes from left to right, all the c's in that rectangle to 0 for any number of points, it suffices to say that the Minkowski sum, the summand in the Minkowski sum drop a lot, so that the association collapses into a lower dimensional thing. Once it's collapsed to a lower dimensional thing, of course, its canonical form is 0 as a d-dimensional thing, right? Later we will see it from string integral. That's even cleaner. So right now I'm just asking you to believe me that from Feynman diagram you have no way. I mean, you can also very laboriously prove it based on all the diagrams, but since it's a summing over Catalan number of terms, it's very hard to see why it will vanish when you set some, because you have to put all denominators together eventually. But association make it totally clear that you have enough c set to 0, this picture collapses to low dimension. Now, what's factorization near 0? That's more interesting. Let's explain that. Okay? So When I say near 0, is that within a rectangle, if I set all the C to 0, the amplitude vanishes. But if I turn on one of them, just one of them, the amplitude will not vanish now, right? Otherwise, I would find a new 0. But I'm telling you the amplitude goes like that. So, okay? So if I look at a very general endpoint mesh, still with my favorite 1, 3, 1, 4 kind of ray-like triangulation, base triangulation, whatever. So if I go from some 1i here, go 45 degree here, and go back, this guy would be, do the exercise, this guy would be I minus 1n, I think. Okay, this x1i, this is xi minus 1n. If I set all the Cij here, well, let me call it x1a and the a minus 1n. So if I set all the Cij equals 0 when I is between what? 1 and smaller than a, and j is between a and smaller than n, something like that. In this range, if I set all the C to 0, the amplitude vanishes. That's something I'm going to show you later from string amplitude, where I can even say the C goes to negative integer, it also vanishes, right? But now if I turn on one of the C, say it's here, C star is non-zero, okay? If I turn on one of the C, guess what the amplitude will do? It will not vanish. So all the Cij in that range is 0, but one of the C star is non-zero. What would the amplitude do? The amplitude, endpoint trace phi cube amplitude, goes to a 4-point amplitude. Actually, this guy and this guy. So let me write it down. x1a plus xa minus 1n. This is a 4-point amplitude. So it's as if this whole thing collapses into just the one thing, right? One rectangle. Because all the C's are 0, this can be removed from your picture. So you're left with a 4-point amplitude times two things. This is called up amplitude, this part. This is also a mesh for a lower point amplitude. And this is also a mesh for the lower point amplitude. So you have this is called down amplitude, for example. You have an A up and A down. Okay? This is the factorization near 0 picture. Sorry, I can remove all this. It's also easy to see from the Minkowski sum. Although I'm not going to bother you with the details, you can imagine that if I set enough C to 0, the whole thing collapses. But right before I set the last C to 0, say I turn on one of the C, it won't vanish. It will become some lower dimensional facet times the height, right? That height, that line interval is this guy, is the 4-point guy. And its top and bottom facet will be these two amplitudes. Of course, there's some detail that which C star I turn on will determine this kinematic dependence of the A up and A down. Also, I'm not going to go to the details in our paper that essentially this portion of the up amplitude and this portion of the down amplitude, their axis will be let me see, will be shifted, will be changed to some other, because all these C's are 0. So this will equals that and this will equals that. So there's some shift in the definition of their up and down amplitudes, but otherwise it's always true. So depending on which C star you turn on, this up and down amplitude, which are always those lower point amplitude, but with will have slightly different kinematic variables. Okay? So I can give you examples. For example, for 5 particle, this expression, remember I told you this expression vanishes when you do this. What if I turn back on the C13? Okay? So this expression, I'm only turning off C14, not C13. C13 is non-zero now. What if I do this? Now this expression, you can look at here, right? Its down amplitude is 3-point. It's nothing. Its up amplitude is a 4-point, except that this point is, anyway, this point is fine. So the 5-point amplitude A5 trace phi cube, when I set C14 to 0, becomes, so remember this is 1, 3 and 2, 5, right? So this is x13, x25. That's the 4-point line interval times the 4-point up, which is given by 1,4 and the 3,5. So that's the up amplitude. The up amplitude, you need to remove the 1,4 here, and 3,5 is still here, no problem. So 2,4 is changed to 1,4 times the down amplitude, which is 3-point. So it's 1. Okay. Okay. So this is more interesting. This is telling you not only there's a 0. If you turn on one of the C, the amplitude factorizes into a 4-point times 2 lower point amplitudes. Of course, I'm explaining a lot of things that I hope you just get the feeling that from Feynman diagram is completely, it's very hard to see these kind of things, but from the Surfaceology, although I didn't show you the detail, you just believe me that the Minkowski sum picture made it totally obvious. Later I will show you the proof from the string amplitude. So that's one thing. You may ask me, what's the point of going to, I mean, for string you may understand, oh, the U variable, very nice, blah, blah, but what's the point of taking field theory limit and write it as a tropical integral which still contains Catalan number terms? That's one of the points. Once you see that it's a single object, you can explore many things, right? For example, you can also ask what are the large n limit of this amplitude. Viewing it as a single object makes a lot of things obvious. So this is a new property we discover about phi cube amplitude. You may still object saying, what's the, well, let me give you the final, sorry, let me give you the final example, which is 6-point amplitude. I'm just writing down an example. You can go check yourself. For example, when C14, C25, C14, C15, C25 all goes to 0. So I'm looking at this yellow rectangle, it's yellow square, but I'm turning on one of them, like C24 is turned on. Now it's interesting because this yellow rectangle has both up and down, both 4 points sitting there. So the amplitude actually going to the product of three 4 points. One is 1,4 plus 3,6. That's the 1,4, 3,6. That's really the the line interval that's always there. And then you have the A up, which is 4-point, 4-point A up, and the 4-point A down, right? So the 6-point amplitude, which has 14 terms, very nicely become this product of 4-point. Actually, I can tell you that we can always choose some kinematics so that the amplitude is given by product of 4-point. This is called like maximally splitting. You split into the end as like a cube, right? It's always products of line, or the product of beta functions for the string integral. Okay, so up to this point, you can still not be impressed at all. You say, okay, you find many things about phi cube. Who cares about phi cube? Especially it's tree level, right? So one thing I would say is that there is a totally canonical way of generalizing this 0 and splitting condition. Actually, not exactly the factorization near 0, but something even more fundamental called 2-split to all surfaces. Okay, so to all surfaces there are such conditions that the field theory or string amplitude will split into 2 or even 3 objects when you do, or even more objects, is by going two smaller surfaces together. I won't go into that part, but now I'm going to turn to other theories. Question?
Does this splitting happen only because there is necessarily one of the Cij?
If I turn in more Cij, it's getting even more complicated. So this is the minimal away from 0, right? So I turn on. So okay, sorry, I forgot to say. Very good question. So actually, I don't need to tell you about 0. I just tell you about this behavior, that within a rectangle, only one C is non-zero, other are 0. It will develop up, down, and this guy. Now you can derive 0, because the 0 is what? The 0 is the 0 of this guy, this 4-point guy. So the last Cij is nothing but the sum of these two x's, right? So that's why 0 is a consequence of this splitting or the factorization. Yeah. If I turn on more, then it's more complicated. So it's a very good question, because I don't think anyone studied so like further away from 0. What can you say in general, right? So I know Nima and the friends, they've been doing something like still spatial kinematics, but quite away from zero, they can predict how the amplitude behavior still looks very simple, like product of 4 point at large n, at n goes to infinity. In the large n statistic case, they can work out that thing. But there's something in between, I think. One side is for any n, you can have 0 splitting and 0 and 2 splitting, 3 splitting. But the other side is large n. I would like to explore something in between. Yeah. So let me end with just two sentences, 2 claims. Exactly the same appear for here. So for those of you who are not very familiar with this series are 2 mostly studied colored particle amplitudes in the last years. I mean, from CHY, from Goldstone. Of course, Yang-Mills, I don't have to say anything. I mean, it's extremely important. But for non-linear model, it's also very, very important. It describes you the Goldstone particle when you have symmetry breaking. Is really the leading order of the chiral Lagrangian, right? So this is like a first term in the effective field theory expansion. And this is a colored particle with 2 derivatives. So it's very different from trace phi cube. Trace phi cube has only denominators. This is the Feynman rule of this goes like for any even point, there's something proportional to like PA dot PA plus like plus 3 and PA dot PA plus 1, PA dot P. So anyway, the Feynman rule goes really like SAA plus 1, SAA plus 3. There are different terms, right? SAA plus 5. So for example, for 4 point, there's only a contact term. So the 2 derivative interaction give you S plus T. That's or you should be familiar with this notation that now the 4 point amplitude is just a contact term with this 2 derivative interaction. It's just 1, 3 plus 2, 4. Yeah, I'm telling you this. I'm saying that this theory is very important. And then for 6 particle, you can have this kind of factorization, or I draw it in a hexagon. So 1, 2, 3, 4, 5, 6. You can have this kind of factorization where you have a pole x1, 4. And then you have 2 4 point. The first 4 point, again, 1, 3 plus 2, 4. The second 4 point is something like 1, 5 plus 4, 6. And then you have cyclic 2 terms. The hexagon has 3 such things. And then you have a contact term. You have a 6 point contact term, which goes like minus x1, 3, minus x2, 4, and so on, okay? Plus cyclic. So I'm just showing you this 4 and 6 particle amplitude to give you a flavor of this thing that people have studied Adler zero and so on for this class of Goldstone particle theories of Goldstone particles. And this theory is very special. It's a special Goldstone. It's the analog of the gluon in this world because it can be uniquely determined by Adler zero. So Adler zero just says if you take any particle, momentum of any particle to be solved, this amplitude will vanish. Just requiring that, it will determine the thing, determine the full amplitude. Then of course, Yang-Mills scalar, I don't have to say anything, right? So you just start with the original Yang-Mills Lagrangian, chase F mu nu. I'm just telling you the theory, and then you do a dimension reduction. There's the phi square a square term with derivative and so on, and then there's a phi 4 term that you dimensionally reduce your gluon down to some scalar. So in both these theories, if I consider so in this theory there's only pion. In this theory there are gluon and the dimension reduction of gluon, those scalar particles that correspond to gluon. If I consider 2n scalar amplitudes in both theories, let me end it here, that they have exactly the same zero condition and factorization near zero as the phi cube. Okay, so this is totally surprising because this amplitude looks nothing like phi cube. It has all these contact interactions, very complicated numerators. Why on earth, if I set this something that belongs to the ABHY world, the Surfaceology world, why on earth would I when I set this to 0, the whole amplitude, including numerator, will vanish. So this is the first time you start to see that just by considering surfaces with trace phi cube kind of very toy model theories tells you something about the real world, about pions and gluons. Okay? Here is still not exactly gluons. Here is a 2n amplitude, 2n scalar amplitude that contains n gluon amplitude in it, right? So if I consider so this dimension reduced Yang-Mills theory has scalars in pairs. If I consider this amplitude with like 1, 2 in a pair, 3, 4 in a pair, 5, 6 in a pair, everything is still color ordered. Then this 2n scalar YMS amplitude contains in it a gluon amplitude, because that's the only interaction, right, with 2 phi and the A that sitting here. So I'm looking at the outside guy. I'm saying, okay, if I set all this C to 0, the whole Yang-Mills scalar amplitude will still vanish. And if I turn on one of them, it will start to factorize. Okay, so this seems to be totally general, and in the next lecture, I will start to explain all of them using string integral. And it's very surprising, why would I use string integral? It turns out that for this guy, it's fine to use phi cube, but for this guy, you have to use string integral because it's related to the, not directly to trace phi cube, but to stringy trace phi cube. Okay? And then this idea will generalize. For this is kind of trivial that to all loops, the pion amplitudes are exactly containing all loop phi cube amplitude without the stringy thing. So this is like a nice surprise coming out of a byproduct coming out of our study, because there's been a lot of study of tree amplitude in this theory, but not much about this loop integrand. Now you say, okay, don't forget about study the loop integrands of NRSM. Just go to phi cube, you figure out the all loop integrands of phi cube, you're done, because it's containing it. It's literally given by a kinematic shift. For this story, it's much more non-trivial. I think it's still ongoing. This research is still ongoing, that you want to extract n gluon amplitudes from 2n point stringy trace phi cube, not trace phi cube itself. It's easy to understand because it's not scalar theory. It's really spin 1 particle. How do you extract gluons out of 2n trace phi cube? It's impossible, but you can extract it from something that I wrote there or here. Just to all loops, you can slightly shift this stringy trace phi cube integral and produce n gluon amplitudes or all loop integrands out of it. Okay, so I'll stop here, and if there are more questions, take more questions.
Please ask questions.
Yes.
Okay, since nobody else is asking, is the reason why you're considering 2n scalars is because you want to get rid of the polarizations?
Very good. So for pion, there's no like immediately the pion has only even multiplicity amplitudes, right? So to compare, to say that I have a pion amplitude that shared is 0, I have to consider 2n scalar case. Compare with that. Actually, later you will see that also the odd number of cases will lead to some pion coupled to trace phi cube. For gluons, yes. So for Yang-Mills scalar, it's the same. You have to have even number of scalars. That's the definition in the flavor structure, that you cannot have odd number of particles. But later you will see that exactly as you said, that the general idea, even beyond just the zeros and factorization at tree level, is we want to replace every gluon by a pair of scalar to all loops in the same sense. So the gluon polarization will be represented by some momentum, the difference of these two momenta of the external scalars. Yeah. So that's the main idea. I can talk later. So you have to, yeah, exactly. You have to work with one pair of scalar for each gluon. Yeah, I mean the last thing, and the last part, I'm just sketching what I'm gonna talk. I haven't go into any detail. Yeah. So to summarize, the nonlinear scalar model story is very nice, but it's really simple. It's really just the observation that the study trace phi cube has one extra value, which is give you all loop nonlinear scalar model. But for gluon, it's very non-trivial. For gluon, you have to go to all the full stringy things with 2n scalars. That's necessary to, yeah. Okay.
Any other question?
My question is, for the stringy trace phi cube amplitude, is there any additional poles where xc goes to some integer value instead of 0?
Very good, very good. So I think this is, again, an open problem, even at tree level, although in general we understand it. So when we say this guy goes to, this guy represents a string amplitude, of course you guys know that this guy has, it has poles when xc goes to -1, -2, and so on. Those correspond to higher level things, right? But since it's not precisely clear how, so where this live in the space of our string theory, so for example, already at tree level, when you study xij goes to -1, -2, this gives you same factorization in picture sense, but now the exchanged particle has spin. But it's a mixture of things in general. If you go to x equals -1, it has as a spin 1 together with a scalar. If you go to x -2, it has spin 2, spin 1, and scalar, right? So the gluon idea is very similar to this. This shift I'm gonna tell you that allows you to go from stringy phi cube. So in one sense, gluon containing stringy phi cube is not so surprising because if you go to level 1, it is a spin 1. But the key is that there's a very simple shift that allows you to only have gluon in the internal. So I think this is a very beautiful question that no one has studied systematically, which is if you go to xc equals -1, -2, and so on, even just -1, forget about higher, what is the general behavior? We know the general behavior should be the same picture that the surface should factorize or go to single cut, but what precisely propagating there? It's a mixture of spin 1 and spin 0, but for all higher surfaces, this is not being studied as far as I know, yeah.
If there is some urgent questions, if not, we will continue in the 11:30. So let's have a break.